Hey guys, welcome to CakeWalk Cambridge. I'm Aisha and you're watching Chapter 1 of IGCSE Chemistry 0620, The Particle Theory of Matter. So I'm finally starting IGCSE Chem and I'm so excited because this is something that so many people have actually asked me for in person. And yeah, let's get started. This is an easy chapter and so we should finish it pretty quickly. Okay, so the first thing that your syllabus requires you to know is the differentiation between solids, liquids, and gases. So when it comes to shape, solids have a fixed shape. For example, this book, fixed shape. Liquids take the shape of a container. So if you have a container that is star-shaped, like it has a star-shaped base, then the liquid will, when you pour the liquid in, it'll have a star shape as well. If you have a circular cylindrical container, then it'll take a cylindrical shape as well. So shape of container. And gases fill up a container. That is, if you have a small little box and like that has gas in it, the gas will spread out to fill up the little box completely. And then if you kind of use a vacuum and take out the gas from the box and put it into another larger box, it will spread out and also fill up that container. Okay, so gases have no fixed shape. Volume, solids have a fixed volume. Now, what exactly is volume? Volume is the amount of basically it's pretty much the amount of space or the amount of matter, the amount of space that matter takes up. So if you have this book, for example, this book, okay, has a certain volume. Let's say it's like 50 centimeter cube. If I open this book, it'll still take up 50 centimeter cube. Okay, because here, if you look, okay, over here, the width of this book, okay, is this much. But when you open the book, the width decreases, but then this flap also takes up space. It takes up the same amount of space that it would have taken up if it was joined together. So the volume of a solid is fixed. It does not change, okay, because the shape is also fixed. Here, then again, for a liquid, the shape is fixed. The volume that it takes up will be the same. For example, if you have a measuring cylinder that's really narrow and tall, um, like let's say the liquid, like I'll just draw it out for you. Supposing you have this kind of measuring cylinder, and if you have like 20 centimeter cube of a liquid, it'll take up this much space, which is 20 centimeter cube. And if you have a short, wide measuring cylinder, it'll take up probably this much space, but this is also 20 centimeter cube. Okay, so liquids will take the shape of a container, but their volume will be the same. Okay, so the volume is not going to change no matter how deep, wide, or whatever the container is, the volume will be the same. If it's a wider container, the liquid will be less deep, the height of the level of the liquid, but it will take the same volume as that in a narrow, taller container. And gas is again not fixed. If the shape of a gas is not fixed, that means if the gas can spread out to fill a big container or be compressed to fill a small container, that means the amount of space that it takes up, the amount of space that the gas particles take up will keep varying. So again, the volume varies. Forces of attraction are what are forces of attraction? Forces of attraction are basically um, forces like electrostatic forces that um, pull the molecules, okay, of a state of matter to each other, closer to each other. That's a force of attraction, okay. So basically in solids, they're obviously the strongest. Now, how can you like justify that they're the strongest? The shape of a solid is always fixed, which means that the forces of attraction have to be really strong. Because if the forces of attraction are weak, then you can obviously like change the shape of a solid, but you can't because the particles are held tightly together. Okay. Now in a liquid, liquids flow. That means you can change their shape. You can empty them out into different containers and their shape will change. Which means that forces of attraction are weaker than of solids. But can you say they're very weak? No, why? Because the volume is always fixed. So there is only a certain amount that the forces of attraction that the particles can move apart from each other because they can't like completely change volume or like increase or anything. The volume is always fixed. So there are forces of attraction that are significant, but they are not strong. They're significant. And then in gases, obviously, they have the weakest forces of attraction because the particles of a gas can move far apart or come close together. But we're going to just look at moving far apart right now because gas particles can move really far apart. The forces of attraction that pull them together to each other have to be the weakest because the volume varies. Okay. Then you have distance between particles. Higher the forces of attraction. Now this is the correlation. Stronger the forces of attraction, lower the distance between particles, lesser the distance between particles. Okay, because the force of attraction pull the particles close to each other. Therefore, the distance between them decreases. So solids have the least distance between particles. Liquids have a moderate distance between particles. That means there is some distance between them, but it's not going to change that much. Okay, like there is a little distance between them, not too much. Okay, and gases are obviously furthest apart. That's if you're putting them in like an open container or something, then the gases will spread out. But generally, because they have the weakest forces of attraction, the particles can move far apart from each other. Arrangement of particles. Now, a lattice is basically a three-dimensional arrangement, okay, which you will also learn about in chapter 3. But for now, you just need to know that the particles in a solid are held together by a three-dimensional lattice. Liquids have no fixed arrangement. Why? Because they take the shape of container that they are placed in. So there again, there's no proper arrangement. The particles just keep flowing and sliding. And gases again have no fixed arrangement because they spread out, they get compressed. There's no fixed volume, no fixed shape. Movement of particles. Solids vibrate to and fro in a fixed space. Why? Because they have the strongest forces of attraction and they are held together in a lattice. So they just keep vibrating in that one fixed place. Okay, they don't move. Liquids slide over each other, and that is what causes the motion like of liquids to flow. Their ability to flow is caused by the particles of liquids having the ability to slide over each other. And gases random collide with each other and bounce off their surfaces of colliding and then collide with the walls of the container that they are in and then bounce off those surfaces as well. So they have random collisions basically. Particle energy. Now obviously the state of matter that has the least motion, okay, amongst particles will have the lowest kinetic energy as well. Now you see gases are always moving, colliding, they have no fixed arrangement, they're farther apart. The force of attraction are weak, which means their particle energy is the highest. Solids have strong force of attraction that hold them together, and all they can do is vibrate. So they have the least particle energy. And then liquids again moderate. So I'll give you an example. Supposing you have less energy, okay, on a day that you've eaten less, okay, and you've gone to the gym and you're lethargic, you're not gonna do much. You're probably gonna do like a few exercises, a few workouts, and then leave. Okay, that's because you have less energy. You don't move around much. You want to sit in one place. You don't want to do too much work. But if you go to the gym on a day, you have a lot of carbohydrates and you're like and proteins and you're ready to work out and you have like energy, then you'll obviously move around more. You'll finish more machines. You'll do more work. You will move. There'll be a lot more movement, a lot more action on your part. So therefore, particle higher the like more movement, more particle energy, weaker forces of attraction, and that's how they're all correlated. We also have to like learn how to draw the particles in a container. So usually they give you like rectangular boxes and you draw them. So like supposing this is one rectangular box and you have to draw solids, you have to draw solids in this way. You draw like and ensure the particles are all the same width and all. You don't really have to use a compass, but I used to use like a rounder compass and pencil while drawing. Ensure they're like stuck together, same proportion, same width, little circles. Okay, so you like that you draw 8. That's how they're gonna look. Then if you have a liquid, again you will need to show like some space, but also that there are forces of attraction, so they can't just be far apart. So you'd probably draw them like this, but like basically no, like there's a little space between them, but most of them are clustered together. And there is no real arrangement. Like if you see here, there are like 2 neat rows. Here, there's not going to be any rows. They're just going to be like together in random places. And that's how you know it's a liquid. Sometimes they'll draw it for you and make you identify. And you have to like identify if there are like neat rows. The rows kind of tell you it's a solid. And then if you have a gas, draw a little box there. Gases is the easiest. It's supposed to be random, but pretty much everyone draws it like this. One particle in every corner of the box and one in the center to show great distance and like the fact that they're far apart and there's no forces of attraction, and it's random. That's why you draw it like that. Okay, moving on. Okay, so now we have to learn about different processes. Now you have to also be able to describe them using the kinetic, using the particle theory of matter, and that's really easy. They all have like the same fundamental steps. You just have to use them and apply them differently. So now melting, you have a cube of ice that you place out in summer's heat in Mumbai, or anytime actually during the year, it's gonna melt into a puddle of water, and that is melting when it changes, when state of matter changes from solid to liquid. So there, what really happens, and usually when you're talking about melting, yes, it can happen without a heat source, but usually in chemistry, IGCSE, when we talk about melting, we're gonna imagine that the substance is being heated. Okay, you need to remember it's solid to liquid. Sometimes they ask you, like, which states of matter take place and what does it change from. Like, it's such easy 1 mark questions. You can't lose marks here. So melting. So first the solid is heated. You have a heat source. The particles of a solid gain energy. Now, what did I tell you? Gaining energy, the higher the energy, the lower the forces of attraction. Because the energy allows the particles to move, and when they move apart. So when the particles have more energy, they have more, like, so basically when they have more energy, they are able to move further apart. So the distance between them increases and the forces of attraction between them decreases. Okay, because they are not attracting each other anymore, like moving further apart. So the particles gain energy, they start moving faster, higher kinetic energy. Kinetic energy is movement energy. So they start moving faster, they start vibrating faster. The bonds between them, which is basically forces of attraction, you can use bonds or forces of attraction, between them are weakened due to the energy supplied to them. Now, what happens when the forces of attraction get weakened? The particles move further apart. They're not attracted to each other that strongly anymore, and then the particles have enough energy to slide over each other. And which state of matter has particles that slide over each other? Liquid. So the substance is now officially a liquid. Okay, that's just how easy it is. Freezing is basically liquid to solid. You have an ice tray, you pour water into the ice tray, you put it back into the freezer, and then voila, and sometime you have solid ice cubes. So you have a liquid that is cool. Now here the source of cooling is the freezer. The particles lose energy. When they are cool, that means energy is taken out of them. So the particles lose energy. They lose kinetic energy, so they lose movement energy, so they move slower. Bonds between them are now strengthened. Because they move less, the forces of attraction between them can get stronger. Because there's less energy, to break the forces of attraction are stronger now. Okay, so the particles start moving closer together. Basically, the particles don't have energy, so as I gave you the gym example, they move less. So they move closer together and then they start vibrating in a fixed position due to stronger forces of attraction. Substance is now a solid. Sorry, this is a mistake. Solid. Okay. And you need to remember this process with the keywords like bonds or force of attraction, movement, energy, vibrating, closer together. So their speed of movement and the distance apart that they are while moving is important in your answer. And always write these answers in terms of energy. They're losing energy, gaining energy, and then bring about forces of attraction. So you first talk about energy, then you talk about forces of attraction, and then you talk about movement, like the speed of movement and the position of movement. Okay. Then we go on to boiling, which is liquid to gas. You have water in a pan, you put on the heat, it starts boiling, bubbles rise to the surface, they burst, a gas is formed. Okay, so I'm going to give it to you a little more scientifically. A liquid is heated. Now, boiling, in terms of boiling, you will always talk about a heat source. Boiling always has a heat source, always. Okay, so a liquid is heated, the particles gain energy. Now, what happens when the particles gain energy? They they start moving, right? They start moving more because more kinetic energy. More kinetic energy, more movement energy results in more movement. Don't write movement energy in your paper. I'm just giving it to you like to understand, okay? So particles with the highest energy rise to the surface of the liquid. So supposing this is a pan of water on the stove, if you have this particle that has high energy, it's going to rise to the top. Okay, and when it rises to the top, it forms a little bubble. Yeah, now what happens is these bubbles burst. When these bubbles burst, the particles escape into the air as gas particles. That's how they change from liquid to gas. And the energy supplied here by this fire fire, helps to weaken the forces of attraction between the particles. The substance then becomes a gas. Again, you see, you first talk about how it's heated or what happens to the substance, the original state of matter, the particles, what happens to their energy levels, movement, then what happens in the process, and forces of attraction. These key points, these 4 key points have to be there always. Okay? And don't forget, liquid to gas, boiling. Now we move on to condensation, which is gas to liquid. Same thing but in reverse. A gas is cooled. Okay, when you're having a shower and then you see like little droplets of water in the mirror. Why? The mirror has a cool surface, so water vapor in the air, basically when it touches the surface of the mirror, it gets cooled. The gas is cooled. The particles lose energy. They come closer together. Movement becomes slower here. The particles stop moving fast. That means slower movement. So they come closer together, which is also a result of forces of attraction strengthening between them due to lack of energy. Energy is taken out of them. So less energy is used to break the forces of attraction. So the forces of attraction are now stronger. The particles move slower and they come closer together. They start sliding over each other instead of bouncing off the surface of each other and colliding. So the substance is now liquid. Easy. Next. Sublimation. So this is basically gas to solid or solid to gas. Same thing, a solid is heated. The heat provided is extreme, and so it is enough to supply particles with energy to skip the liquid stage. So the heat that is provided to the solid is so much that the particles in the solid don't like first gain energy and start sliding over each other. They immediately start bouncing off the surface because it's like that much heat that is supplied to them. And so the particles start like colliding with each other and bouncing off the surface, and so they become a gas. And the forces of attraction are weakened to a huge extent. Okay, and that's how they become gas particles. I have not seen this in the 2023 syllabus, so I'm not sure if you will have it, but I had it and it was a significant part of my chapter, so I'm just gonna teach you. And I think it's good like knowledge. Like I taught my 8-year-old cousin this recently and he enjoyed learning, so I think this would be like why not? If you want to skip it, you can skip it. Okay, evaporation. Now, evaporation is basically the same process as boiling because it's liquid to gas, but it is without a heat supply. So if you have like a puddle on a rainy day and then the sun comes out and then the puddle like disappears, it doesn't disappear. The water in the puddle evaporates to form a gas and the ground becomes drier because the liquid has escaped as gas particles. And that evaporation, if you realize, has happened without a heat supply. Like it's just like the sun, but it's not really a heat source. Like there's no like fire or anything that's causing it to change state of matter. So the liquid absorbs thermal energy from sunlight or natural heat sources. The particles gain energy and move faster. They move further apart, and forces of attraction are weakened. They reach the surface of the liquid. So the particles from the bottom reach the surface of the liquid, and they escape as gas particles. That's it. That's just it in evaporation. Not seeing this in your syllabus, but I think it's good to know just in case. The difference between boiling and evaporation. First, we're going to talk about a heat source because we already discussed it. A heat source is required for boiling, but for evaporation, you just need natural heat sources or the sunlight. Temperature. The temperature when you boil a substance, or basically when any change of state of matter is occurring, we're going to go to that next. The temperature always remains fixed. Okay, so for boiling, because it's a proper change in state brought about by heat source, like it's brought about manually, that's why the temperature is gonna like it's gonna be at a fixed point. Boiling occurs at a fixed point. Like water boils at 100 degrees Celsius. Okay, water boils at 100 degrees Celsius, but water can evaporate over a range of temperatures. Like if you look at the puddle outside, it's not 100 degrees Celsius outside when the rainwater evaporates. It's not. So evaporation occurs over a range of temperatures, but boiling occurs at a fixed point, like 100 degrees Celsius, or ethanol I think is 78 degrees Celsius. So it's like a fixed point. Bubbles are present when there's boiling. Bubbles are not present when there's evaporation. That's important as well. All these three are valid points. I usually go for the first two when I write my answer. Now we're going to look at heating curves and cooling curves. So this is a heating curve as you can see because the temperature increases here. Temperature goes from 0 and then increases. This is a cooling curve because the temperature decreases. So basically when a process happens like melting, vaporization, which is basically like boiling basically, or condensation or freezing, like the first 4 processes we spoke about, the temperature always remains fixed. Okay, it just, if you can see here, it's a stable line. Okay, it's absolutely horizontal, it's fixed. This is because the substance is absorbing the energy, or releasing the energy, or letting go of the energy to change state. And when the change of state is happening, when there are two changes of, like when there are two states of matter present during this process, the temperature is always going to remain the same. Okay, so here you have a solid. You heat the solid. Here there's only solid, right? Because you're heating the solid. But as soon as melting starts, okay, there is a solid and a liquid that are present, because some of the solid is transforming into the liquid. The melting point has been reached. Like water melts at 0 degrees Celsius. So let's say this is 0 degrees Celsius. Um, it is being heated, like it is melting, like it is changing state. So the solid is absorbing the energy to become a liquid. Now all the liquid is formed at this point. Here there is only solid. I'm going to draw it in like green. Here there is only solid, and in red there is only liquid, and in between them there is both. So usually they'll like number, or like label these every point of a heating curve or cooling curve, like A, B, C, D, E, and F, and they'll ask you like which states of matter are present in each point. So at A, there is only solid. At B, there is only solid. At C, there is liquid. At D, there is liquid. At E, there is gas. At F, there is gas. But if we have P over here and Q over here, P has solid and liquid, and Q has gas plus liquid. So every time you have like a completely horizontal line, you have to know that a process is taking place, which is either melting, boiling, condensation, or freezing, not evaporation, because evaporation occurs at a range of temperatures. So here you can see it's a fixed point. Here it's a fixed point that melting is occurring at. But if we had to draw it for evaporation, or like here there's boiling, which is a fixed point. Evaporation will probably happen like this, like it's no fixed point. It happens over a range of temperatures. Okay. Okay. So here, okay, same thing. And okay, you have to know, if you're starting with a solid, the first horizontal line that you see on a heating curve is going to be melting, and the second horizontal line that you see is going to be freezing. But if you start a heating curve with liquid, the first and only horizontal line is going to be boiling. Okay, you need to know that. Then in a cooling curve, energy is being lost. So of course, you start off with the gas because it has the most energy. This part only has a gas. Then when enough energy is taken out of the gas, when the gas is cooled enough, it starts becoming a liquid. Condensation occurs at a fixed point. Again, horizontal line. Then the liquid is cooled. At this part, there is only liquid. Now, this is essential to memorize. You have to memorize this, and this is in your syllabus. It's very important. So there's only a liquid, and then after that, freezing starts occurring. Okay, and then there's only a solid. So if you have a cooling curve that starts off with the gas, the first process is obviously going to be condensation, and the second process will be freezing, the second horizontal line. But if you start with the liquid, the first and only horizontal line of the cooling curve will be freezing. Okay. So this is important. I think you might have a few questions about this. You can leave it in the comments or email me. But I think I explained it okay. But yeah, if you have any questions, let me know. And practice like past paper questions for this. It's important. Now you need to basically understand pressure, temperature, and volume. This is a formula in physics, IG physics, but I'm just going to explain this to you. So here you have two gas cylinders, okay? In one, this is where the stopper is, and in one, the stopper is even closer to the bottom than before. So you have 5 gas particles in each setup. Now the 5 gas particles here have a lot of space. And what I tell you before, they will fill up all the space of the container that they're in. So they have a larger volume, correct? Because there's more space, they've spread out and they have a larger volume. So they collide with each other less frequently. Pressure is basically brought about by particles colliding with each other. So when they collide with each other less frequently, that means pressure is less, correct? But here, the pressure of the gas has been increased. Now, why? This is because the stopper has been pushed even lower, bottom. So that means there's less space for them to move into, which means they bump into each other more often. So that means there's higher pressure. Okay, so, and there's a lower volume. Volume is basically the amount of space that matter takes up, right? And here it takes up more space and here it takes up less space. Gases don't have a fixed volume. So the volume decreases and pressure increases. As you can see here, volume goes to half and pressure doubles. Okay. Um, like I'll give you an example. If you have a small classroom and you're walking around with your friends, or a small playground, a small football court, small football pitch, sorry, and you're playing football, there's more likely to be collisions between you and your friends while playing. But if you have a bigger football pitch, you're more spread out, there's more passing, long passing, then there's likely to be less collisions. So the small football pitch is basically for a smaller volume. More collisions between y'all means there's more pressure. But if you have a larger football pitch, that's larger volume, so less collisions between y'all, so less pressure. So pressure and volume are inversely proportional. Temperature, again, temperature. So when you heat a solid, it becomes a liquid, correct? What happens to the particles? They gain kinetic energy and they start moving further apart. Okay, basically they start moving more. But if you place them in a container, okay, if you heat a container with fixed volume of gas, okay, then the particles start moving more and they start like collide. They start basically the force of attraction between them are weakened because you're providing them with energy, so it breaks the force of attraction, so they start moving more, but there's no more added space to move into because the volume of the container is fixed, the container is closed. So they start colliding with each other and with the walls of the container, which causes a greater pressure. Okay. Now we're going to talk about the effect of changes in pressure and temperature on volume. Here, before we spoke about like what happens in a fixed volume or like the volume changes, but like when we vary the volume. But here now we're going to use pressure and temperature as independent variables and volume as the dependent one. So if you have a high pressure, the volume decreases. Supposing you have a syringe and you push the stopper down to increase the pressure, the volume of the gas decreases. Why? Because particles are forced to move closer together. Now, if you remove the pressure by taking the stopper out, there is more space for the particles to move into. So the volume increases. They take up more space. They spread out more. If you have a syringe that basically where the stopper can move, it's not in a fixed place, and you heat the syringe, the particles of gas gain energy, the forces of attraction weaken, and they move further apart. So the volume increases. But if you cool that same syringe, then the particles have less energy now, stronger forces of attraction. They are pulled closer together. They move slower. So the stopper will move like towards the bottom again. So the volume decreases. Okay. That's how temperature and pressure can affect volume as well. Brownian motion. Brownian motion is basically, just remember this, random motion arising from larger visible particles colliding with smaller invisible ones. These are two classic examples. And for Brownian motion, that's all you need to remember. These three, and you need to remember the drawing. So I'm going to explain this to you. Supposing you have water and this is a pollen grain. If you look at a pollen grain in water or any small object in water, you will see it moving slowly and moves in a random zigzag kind of way. So zigzag motion is important in Brownian motion. You see it moves like this, then it moves like here, and the arrows show how it's moving. So when you have to draw this yourself, always remember to use a ruler to connect the different circles and use arrows to show the direction. Okay, you ruler and arrows, and this is like one section of water, and you can see the pollen grains moving like in this random zigzag path, and you wonder why. Well, it is because of the water molecules themselves sliding over each other and around each other. Because they slide, they disrupt the movement of the pollen grain as well. So the pollen grain can never be still because it's obviously going to be collided with by water molecules that are going to constantly be pushing it around. Okay, and because the water molecules slide, the pollen grain has zigzag motion. But here you can't see the water molecules moving. You can only see the pollen grain moving. That's why it's called Brownian motion. It's random motion. That's the zigzag motion. Random motion of larger visible particles like the pollen grain caused by the random motion of smaller invisible particles like water. So you can draw the same thing, but instead of writing invisible particles of water, you can just write air, and then you can draw like smoke. Like this pollen grain can like be a symbol for smoke, a molecule of smoke. That's basically Brownian motion. And then we go on to the last part, that is diffusion. Diffusion is movement of ions or molecules from a region of higher concentration to lower concentration down a concentration gradient. I have a chapter for this. It's chapter 3 of IG Bio. I really recommend you just watch the diffusion part because it's written in like much more detail and it's explained well. So basically, diffusion only involves ions and molecules, not water. Okay, water moves by osmosis. That's a different process, which you don't have in chem. So movement of ions or molecules from a region of higher concentration to lower concentration. That is, if we have like a container test tube with a high concentration of HCl particles on this side, the HCl particle, and they have no HCl particles here. These HCl molecules, if they're gaseous, they're going to move, or basically anything. We're going to take gas as an example. They're going to move to this side of the container from higher concentration to lower concentration down a concentration gradient. Now, faster rate of diffusion is brought about by higher temperature. Why higher temperature? Because particles gain kinetic energy, which causes forces of attraction to weaken, which causes faster movement further apart. So high temperature, steeper concentration gradient. So supposing this here, the concentration of HCl in this syringe is 0.5 cm cube, and then we have this where the concentration here is 1 cm cube. This is going to move faster to this side. This is going to move faster down a concentration gradient because it has a higher concentration, which means it has more particles involved. Okay. Surface area. Now for surface area, let's say I'm not explain this to you if you've not done bio. So supposing you know that the small intestine, okay, has like villus or villi that basically absorb nutrients. Now, why does it have villi? To increase the surface area. So if you just had this kind of like surface of the small intestine, then like the particles of nutrients would move into the small intestine, okay, from these set locations. But when you have like these little extensions, they can move all from any angle into the small intestine. Basically, when the surface area is increased, there's more um, space, more area for the particles to move down a concentration gradient. Okay, so basically, large surface area increases the rate of diffusion. Smaller particles, again, smaller particles can probably move faster. Also, why? Because they have a lower MR, lower mass. So, if molecules or particles have a lower mass, okay, they'll be able to move faster. Like let's say if you're 20 kg, oh not 20, like that's too little. If you're 40 kilos and you're running a 100-meter race, it is more likely that you're more fit and like it's easy to like push yourself further and to like move faster in that time than if you were like 80 kgs at the same body height. Okay, so lower MR, lower mass, faster diffusion. And that was it with chapter 1, particle theory of matter. I hope this helped you. And if it did, please like this video, share this video, and subscribe to my channel. If you have any questions, feel free to email me. And this is only the beginning. We're going to do a lot more. And I promise you I'll try and make shorter videos. I think I just spoke a lot this time. But I hope it helped you. And all the best. Let's get through this together.